Because vectors hold various types of information, and the dot product can measure similarities or differences between them, it is often employed in the attention mechanism. The attention mechanism is a concept in artificial intelligence frequently utilized in natural language processing. Let's consider a sentence. How about using the title of this slide as an example? We have 4 words in the title, each pair of which has a similarity measure. Together, these words form a sentence. When constructing a sentence, the similarity measures between its words are typically high. Let's add a random word apple next to the title and enumerate each word. The word apple is quite relevant to the other 4 words in the title. Thus, its similarity measure is lower than that of the others. However, the similarity measures between the other words are high. Specifically, the similarity measure between dots and product is higher than the similarity measures between the other words. Let's create a table with 5 rows and 5 columns, where each row and column corresponds to a word in the title. The similarity measure between a word and itself is very high, so I will fill the diagonal boxes with the darkest color. The similarity measure between the words dots and product is also high, but not as much as the self-similarity measure. Suppose the similarity measure between dots and attention is also high. Similarly, the similarity measure between advanced and attention is high. We refer to this table as a similarity map or similarity matrix. The self-attention mechanism or attention mechanism in natural language processing defines this similarity matrix before training. Each entry in the similarity matrix holds a similarity measure, which can be calculated using the dot product. In natural language processing, words are treated as data. Thus, each word in the title is not merely a group of letters, but instead it's represented as a vector in an n-dimensional space. If the similarity measure between 2 words is high, the dot product of the corresponding vectors also has a high value. If the similarity measure between 2 words is low, the dot product has a low value. In the attention mechanism, encoding is achieved through this process. Thus, the dot product is a crucial concept. Let's summarize the concept in linear algebra we've learned so far. Suppose we have an n by n matrix A. Then matrix A is composed of n vectors in Rn. If these n vectors within the matrix are linearly independent to each other, then the following properties naturally follow. The rank of the matrix is n. The null space does not exist. The determinant of the matrix is not 0. And lastly, the inverse of the matrix exists. Let's consider another matrix A composed of n vectors. If at least one pair of vectors within the matrix is linearly dependent, then the following properties hold. There exists a null space that cannot be spanned by the vectors, meaning there exists a vector x such that ax equals 0. Moreover, the rank of the matrix is equal to the number of the vectors within the matrix that are linearly independent, and it is less than n. Consequently, the determinant of the matrix is 0. And lastly, the inverse of the matrix does not exist. Let's define the cross product of vectors as well. Suppose we have 2 vectors a and b on a 2-dimensional plane. The cross product of the vectors conveys a directional information between them. Now, consider a 3-dimensional space with vectors x, y, and z on each axis. In this three-dimensional space, there exists a vector perpendicular to both vectors x and y. Vectors x and y are already perpendicular to each other, and vector z is perpendicular to both vectors. Calculating the cross product of the two vectors x and y is related to finding vectors like z that are perpendicular to both x and y. Suppose the coordinates of vector x is 1, 0, 0, the coordinates of vector y are 0, 1, 0, and finally the coordinates of vector z is 0, 0, 1. By calculating the cross product of vector x and y, we can determine if we can find perpendicular vector z. You can compute the cross product of vectors a and b by computing the determinant of a matrix. Arrange vectors a and b horizontally on the second and third rows of the matrix. For the I component, calculate the determinant of the corresponding 2x2 matrix as y1 z2 minus z1 y2. Similarly, for the j component, compute z1 x2 minus x1 z2. And for the k component, evaluate x1 y2 minus x2 y1 from the corresponding 2x2 matrices. Now, let's delve into the conceptual understanding of this product. Consider two vectors a and b in a three-dimensional space. As previously mentioned, the cross product of a and b is a vector perpendicular to both. Since vectors a and b lie on the same plane, the vector perpendicular to both a and b must extend out of the screen. We've discussed various topics related to vectors and matrices, such as matrix multiplication and the rank of a matrix. Moving forward, we'll delve into the concepts of eigenvalues and eigenvectors. Some of you may already be familiar with the formulas for calculating eigenvalues and eigenvectors, and you can easily find the calculation methods in a linear algebra textbook and other resources. However, in this lecture, we'll primarily concentrate on their geometric interpretations. Mathematically, an eigenvalue, often denoted by the Greek letter lambda, satisfies the equation ax equals lambda x, where a is the matrix and x is the eigenvector. In other words, it means that when you multiply matrix A by its eigenvector x, you get the same vector x back, just scaled by the eigenvalue lambda. Let's expand the equation. Suppose A is a 2x2 matrix. The left-hand side of the equation, ax, is simply the result of multiplying matrix A by vector x. Scaling vector x by lambda is the same as multiplying a diagonal matrix with diagonal entries of lambda by x. Eigenvalues and eigenvectors are values and vectors that satisfy the equation. These are the basic definitions of eigenvalues and eigenvectors commonly used in linear algebra. Let's quickly review the methods for calculating eigenvalues and eigenvectors. We'll rewrite the equation from the previous slide. After subtracting the right-hand side of the equation from both sides, we obtain a matrix 3 minus lambda, 1, 0, and 2 minus lambda multiplied by x equals 0. Now we need to find the values and vectors for lambda and x. This equation can be rewritten as a minus lambda I, x equals 0. We're already familiar with this form. X is a vector that constructs a null space. Additionally, x exists only when the determinant of the matrix is 0. The determinant of the matrix can be expressed as 3 minus lambda multiplied by 2 minus lambda equals 0. Thus, lambda is either 3 or 2. When the value of lambda is 3, A minus lambda I becomes a matrix with values 0, 1, 0, 0. The eigenvector is a vector that returns 0 when multiplied by the matrix. Thus, x is a vector 1, 0, and it's an eigenvector for eigenvalue 3.